Initially, there was an infinitely dense mass of matter, a concentration of everything that exists today compressed into an unimaginably small point. This mass of matter, under intense pressure and energy, underwent a colossal explosion, which led to the formation of atoms, molecules, stars, galaxies, and all the cosmic structures we can observe in the universe today. This explosive event, commonly referred to as the Big Bang, has been the prevailing explanation for the origin of the universe, one supported by physicists and astronomers alike for decades. The Big Bang theory suggests that from that single event, time, space, and matter itself were created, giving rise to everything we know. However, despite its widespread acceptance, recent research has introduced new perspectives, challenging the notion that the universe had a singular, early origin. Some scientists now propose that the universe may instead be part of a grand, cyclical process in which it undergoes repeated cycles of expansion and contraction, possibly continuing this process in an infinite loop. Brian Cox, a renowned physicist and popular science communicator, has also raised questions about the standard Big Bang theory. He argues that the idea of something arising from nothing is deeply problematic. How could a universe so vast, so full of energy and matter, emerge out of an absolute void? This line of questioning introduces an intriguing new element into the long-standing debate. Additionally, research conducted with advanced instruments like the James Webb Space Telescope has revealed evidence that contradicts the idea that the Big Bang marked the universe's absolute beginning. These discoveries lead to a critical and thought-provoking question. If the Big Bang was not the true beginning of the cosmos, then what was? This question opens the door to a deeper exploration of the universe's origins, one that might eventually lead us to a more comprehensive understanding of how everything came to be. Join us on this fascinating journey through the cosmos as we explore the frontiers of astrophysics and the boundaries of the Big Bang theory. We will dive into the latest research, uncover new theories, and attempt to answer this profound question and many more that arise from it. If you are passionate about staying updated with the latest discoveries and theories about the universe, subscribe to our channel, hit the like button, and share this video with others to spread the knowledge. Don't forget to turn on the notification bell so you can be informed as we continue to explore the mysteries of the cosmos. Scientists have spent decades developing a detailed understanding of the universe's earliest stages, encapsulated in what is known as the Big Bang theory. According to this widely accepted model, the universe began as an extremely small, hot, and dense state roughly 13.8 billion years ago. In the initial moments after the Big Bang, the fundamental elements that make up everything around us, atoms, protons, and neutrons, were formed in a matter of minutes. This primordial explosion rapidly expanded the universe, creating the conditions for stars and galaxies to coalesce over millions of years. Remarkably, the universe, which now spans billions of light years, was once no larger than a peach, and the temperature at that time was beyond comprehension, exceeding a quadrillion degrees. This almost inconceivable narrative of a universe born from an explosion of unimaginable heat and density matches consistently with observations made by astronomers today. From the detection of cosmic microwave background radiation, the remnant radiation from the early universe, to the abundance of the lightest elements like hydrogen and helium, everything observed seems to support the predictions of the Big Bang theory. To the best of our knowledge, the universe's evolution as described by this theory perfectly aligns with all available evidence, painting a detailed picture of how the cosmos developed over billions of years. However, despite its apparent success, scientists acknowledge that the Big Bang theory is not the complete story. There are significant gaps in our understanding, particularly when it comes to the very first moments of the universe's existence. The central challenge arises from the limitations of the physical theories we currently rely on. The most powerful tools at our disposal, general relativity and high-energy particle physics, have provided us with an immensely valuable framework for understanding the universe. Yet, when we delve into the exact moment of the Big Bang, the mathematical complexity skyrockets, and our current models reach their limits. One glaring issue is the concept of a singularity, a point of infinite density and temperature at the Big Bang's origin. This singularity suggests that, at one point, the entire universe was compressed into an infinitely small, dense point, an idea that defies our understanding of physics and seems almost absurd. Addressing this profound challenge requires new physics, new ideas that can go beyond the limitations of our current frameworks. We need to develop theories that can not only unify the fundamental forces of nature, including gravity, but also explain how they behave at extremely high energies, such as those present in the early universe. This is where string theory enters the conversation. String theory aspires to be the ultimate theory of everything, a model that unifies all of the universe's fundamental forces, including gravity, electromagnetism, and the nuclear forces, particularly at ultra-high energies. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. In this framework, string theory could potentially offer explanations for what occurred in the first moments of the universe. One particularly fascinating concept that arises within string theory is the idea of the epictetus universe, a term derived from the Greek word for configuration or fire. This idea suggests that the Big Bang, far from being the beginning of everything, may have been the result of a prior event, an event in an earlier universe. In other words, the Big Bang might not represent the absolute beginning of time and space, but could instead be just one part of an ongoing process. This idea has been extended into a broader theoretical framework known as cyclic cosmology. While the concept of a cyclical universe has been considered for millennia, it is string theory that provides the mathematical rigor to support such a model. In cyclic cosmology, the universe operates in a perpetual loop, oscillating between periods of expansion, like the Big Bang, and contraction, leading to a big crunch. This process, according to the theory, could extend infinitely into both the past and the future. The theory of cyclic cosmology was notably advanced by the eminent physicist Roger Penrose, who was awarded the Nobel Prize for his contributions to our understanding of black holes and cosmology. Penrose was captivated by a remarkable mathematical relationship between the early universe, marked by extreme density, heat, and smallness, and the future state of the universe, which will be characterized by extreme coldness, expansion, and emptiness. He proposed that these two seemingly opposite states, one representing the universe's birth and the other its distant future, could become mathematically identical when pushed to their extremes. In this view, the total absence of matter in the future could somehow be the very source of the matter that fills the universe today. From this perspective, the Big Bang is not an isolated event but the inevitable consequence of the previous universe's death, with each cycle of existence giving rise to the next. This idea opens up a fascinating new interpretation of the universe. The remnants of a dying universe, black holes that have consumed all matter and eventually evaporated, leaving behind scattered photons in a cold, empty void, could be the seeds from which a new universe emerges. Although this nothingness might seem empty and devoid of significance, it is still, in some sense, a form of something, a state that constitutes a physical universe, albeit a very different one from our own. The mystery lies in how this seemingly empty, cold universe can give birth to a hot, dense universe like the one we live in. This paradox challenges our conventional understanding of space, time, and matter. The key to unlocking this mystery, Penrose suggests, lies in a complex mathematical technique called conformal transformation. This geometric transformation changes the size of an object while retaining its shape. Through this transformation, Penrose demonstrated that the cold, empty state of the distant future and the hot, dense state of the early universe can be connected, aligning their spatio-temporal structures despite their differences in size. Essentially, he showed that the empty universe of the future and the dense universe of the past are, in a sense, identical in structure when viewed through the lens of conformal geometry. In cyclic cosmology, the universe follows a grand sequence of events, unfolding from an old, cold state to a young, hot state. The presence of a hot, dense universe like the one we observe today is the result of the cold, empty universe that preceded it. However, this relationship does not follow the conventional understanding of time, since in these extreme physical states, both size and time lose their usual meanings. The cold, empty state and the hot, dense state exist on different timelines, and from the perspective of an observer within one of these timelines, the cold, empty universe might seem to stretch on indefinitely. In this realm of extreme physics, time and space are deeply intertwined, and our usual ways of thinking about causality and sequence break down. The implications of cyclic cosmology reach beyond the realm of physics and enter the domain of philosophy. If the universe is truly cyclical, it raises profound questions about the nature of existence itself. How did these cycles begin? What caused the universe to exist in the first place? And why is there something rather than nothing? These are some of the deepest metaphysical questions humanity has ever pondered. While cosmology offers speculative and detailed explanations for the mechanics of these cycles, the fundamental question of the universe's ultimate origin remains elusive. For the purposes of our discussion, we can explore several possible explanations within the framework of physics. One possibility is that there may be no physical explanation at all. Perhaps the universe's cycles simply exist without cause. Another possibility is that the universe has undergone an infinite series of cycles, with each new universe emerging from the remnants of the one before it. In this scenario, the quantum state of each new universe is determined by random variations introduced by quantum mechanics. Finally, we might consider the idea that the universe consists of a single cycle that repeats itself eternally, with its beginning explained by its own end. These possibilities are attractive because they avoid the need for uncaused events or first causes, which have long puzzled philosophers and scientists alike. They also offer a new perspective on the nature of time and existence, suggesting that the universe, far from being a one-time occurrence, is part of an ongoing process that has no beginning and no end. Roger Penrose's idea of cyclic cosmology is influenced by his interpretation of quantum mechanics. In quantum theory, a system can exist in multiple states simultaneously until it is observed, at which point it collapses into a single state. Penrose suggests that each cycle of the universe is influenced by random quantum events, leading to slight variations between cycles. This idea opens up exciting possibilities for experimental physics, as it suggests that we might be able to detect subtle traces or anomalies in the cosmic microwave background radiation, the remnant radiation from the early universe, that hint at previous cycles. The idea of a cyclical universe, once a purely speculative concept, is now gaining traction thanks to advances in theoretical physics and observational astronomy. What do you think? Could the universe truly be cyclical, with no beginning and no end? Let us know your thoughts in the comments below. If you enjoyed this video, be sure to give it a thumbs up, subscribe to our channel, and share it with others to help spread these fascinating ideas. Don't forget to turn on notifications so you can stay updated as we continue our exploration of the cosmos.